Next up is the integral test. All right. So a little while ago, we learned about improper integrals. All right. And the whole purpose of that was because we could learn about them since we are capable of doing limits as n approaches infinity, and we're capable of doing the fundamental theorem in calculus working off of a definite integral. And two, so that we can use the integral test. Right? So the integral test is basically as follows. All right, when we think of the general term of whatever series that we're looking for, we're going to set that basically equal to a function. You know, the function is with n as the inputs. And we talked about that in general at the very beginning of series as well, that we can think of a series or a sequence like a function, all right, where the inputs are n, which is usually 1, 2, 3, 4, 5, 6, 7, 8, the positive integers, and the outputs are whatever a sub n happens to produce. All right. If we think of it in that regard, well, then if f meets certain conditions, we can use the integral test. So the three conditions for f is that it has to be continuous, positive, and decreasing. Okay. So what kind of functions are we looking for that are continuous, positive, and decreasing? We're looking at situations like that. Okay. So that's our classic 1 over n type of, or 1 over n squared. But it doesn't necessarily have to be. It could be e to the opposite of n. Okay. We just need a function which is continuous, positive, and decreasing. Okay. And so we're looking for situations like this. Okay. Now what we know is that the conclusion of the integral test says that as long as three conditions are met, then the series and the improper integral are going to either both converge or both diverge. All right, it's not going to be a situation of one doing one thing and one doing the other thing. All right, they either both converge or they both diverge. All right, so the idea basically is that, hey, we know how to evaluate improper integrals. So if we can correctly convert the series to a function, and then we can find the value of the improper integral, right? Or maybe we can't find the value. But if we can't find the value, then we know that the series is going to diverge. If we can find the value, and the series, the integral actually does converge to a particular value, then we know that the series will converge as well. Now, one thing to be careful of is that the series and the improper integral won't be converging to the same value. Right? So just because the improper integral happens to converge to 1 or 2 or 8 or whatever happens to be, that's not to say that the series will converge to that value. All right? It's just a matter of they both converge or they both diverge, not converging to the same value. So do a couple examples in the next video.